And this is Arcs of a Circle, 10.3 in your books. I thought I would do something a little bit more fun, a little bit less dorky than the 80s video from last time. Besides, can anyone figure out how this music applies to this particular unit? Let me know if you do. Alright, your objectives. To identify the different types of arcs. To determine the measure of an arc. To recognize congruent arcs. To apply the relationships between congruent arcs, chords, and central angles. Okay, so let's start with types of arcs. Center of an arc is the center of the circle of which the arc is a part. Almost sounded like Dr. Seuss there. Central angle is an angle whose vertex is at the center of the circle. Minor arc is an arc whose points are on or between the sides of a central angle. Major arc, an arc whose points are on or outside of the central angle. That's all well and good, but if I just gave you these descriptions, could you draw them? Would you be able to recognize them if they were on the board? Well, let me help you with that after this one. Semicircle, an arc whose endpoints are the endpoints of a diameter. That one's pretty easy, so that's why I kind of skipped over that one. Anyway, let's look at some pictures. Center of an arc. Bam! Right there. Okay? Central angle. Whoop! Right there. Okay, again, look, it's got the radii, it forms an angle. Minor arc, let's start with the central angle, and then whoop! That's the arc formed in between the segments of the central angle. Major arc, we start with our central angle again, and then whoop! It's the outside of the central angle, and a semicircle. Whoosh! There's your diameter, and whoop! There's the semicircle. So hopefully you have a kind of a better idea as to what they look like now. Alright, so the measure of an arc. The measure of a minor arc, or semicircle, is the same as the measure of the central angle that intercepts the arc. We touched on this last unit, so don't pretend like you haven't heard it before. So we've got this central angle of 65 degrees, which means the measure of that angle is what? 65 degrees. Very good. If you got it wrong, not very good. Alright, the measure of a major arc is 360 minus the measure of the minor arc with the same endpoints. So what I mean by that is, okay, so it's got the same endpoints as this. This here is 65. That's not the measure of the major arc. We take 360 minus 65, which gives us 295. So 295 degrees is the measure of the major arc. Okay, now congruent arcs. Two arcs are congruent whenever they have the same measure and are parts of the same circle, or congruent circles. So if we were given that these two circles were congruent, okay, and we had the same arc measurements, we might be able to prove that their arcs are congruent. So here I've got arc AB is 65 degrees, arc CD is 65 degrees. Okay, we can say that they're congruent. This one, say AB was 85 degrees and CD was 85 degrees, and we were told that the two circles were congruent. In both of these diagrams, we could say that AB is congruent to CD. However, here's why you can't say it unless if they're on two separate circles. Okay. Let's say I had a circle here, and this was also 85 degrees. Now their measures are the same, but can we say that they're congruent? They have the same degree measurement, but obviously they don't have the same length, which would mean that they're not congruent. So something you need to keep in mind and be aware of. Okay? Alright, some theorems. Yay, I told you there would be proofs to this chapter. Okay, Theorem 79. Two central angles of a circle or of congruent circles are congruent, then their intercepted arcs are congruent. So let's say that these two angles have the same measurement, then these arcs are congruent. Simple enough, right? Okay, Theorem 80 is the opposite. If two arcs of a circle or of congruent circles are congruent, then their corresponding central angles are congruent. So pretty much the same thing. It's just the opposite. The converse, if you will. Theorem 81. If two central angles of a circle or congruent circles are congruent, then the corresponding chords are congruent. And I know this diagram isn't the best in the world, so bear with me. Okay, and Theorem 82 states, again, the converse. If two chords of a circle or congruent circles are congruent, then the corresponding central angles are congruent. So these are all, it's going to be like 6 theorems, but it's actually only 3. All right, Theorem 83. If two arcs of a circle or congruent circles are congruent, then the corresponding chords are congruent. So you've got if the arcs are congruent, that means that the chords, as long as they're going to the same endpoints that make up the arc, would also be congruent. And Theorem 84 states, if two chords of a circle or of congruent circles are congruent, then the corresponding arcs are also congruent. Okay, so central angle, chords, arcs. Okay, if they're congruent circles, or if it's the same circle and they're congruent, there's all kinds of stuff you can show back and forth. All right, so let's try a practice problem. We are given circle E. We are also given that EF is perpendicular to DC and EG is perpendicular to AB. So we know this, we know that, and we know that EF is congruent to EG. We need to prove that AC is congruent to arc DB. All right. Start with step 1. We have circle E. Well, we've got all our givens. Okay, you can read. Step 2. We have segment DC is congruent to segment AB. Because if two chords, so this segment here, are equidistant from the center of a circle, then they are congruent. That's something that you have not learned. We kind of glossed over that. We didn't really touch on it, but that's something that you're going to want to keep in mind. So if two chords are equidistant, this is important. Make a note of this. This is a theorem. Okay? So if two chords are equidistant from a center of a circle, then they are congruent, and the converse of that would also be true. All right? So make note of this one here. Theorem. But that was about the only useful thing that was in that chapter, and I didn't want to spend an entire video just covering that. So that's why I threw it in here. So again, we can say that DC is congruent to AB. Why? Because if two chords are equidistant from the center of a circle, then they are congruent. Which means that arc AB is congruent to arc DC, because if two chords of a circle are congruent, then their corresponding arcs are congruent. And then we can say that AD is congruent to AD by the reflexive property. Yes, you can use that on parts of a circle as well. And then we can say that AC is congruent to DB by the addition property. Simple enough. Okay.